Welcome to EDU World Space.
So in this problem, we are given the initial starting point of block B and the cart A, and we wish to calculate the speed of the cart A and the block B at this position. So we'll draw a diagram. So cart A is moving horizontally to the right. We'll choose this as positive with momentum ma va. So it has velocity va. Attached to the cart is block B. So we're interested in the point at which block B passes directly under cart A, and it's moving to the right with momentum mb vb. So it has velocity at this point vb. So the first thing we'll do is use the conservation of linear momentum. We know that the momentum when it is released of the system is equal to the momentum as it passes directly under the cart, as the block passes directly under the cart. So since the block and the cart are initially at rest, the initial linear momentum L0 of the system is 0. And as B passes under A, the linear momentum of the system is equal to that due to the cart ma va plus the momentum due to the block mb vb. So if linear momentum is conserved, this means that ma va plus ma plus mb vb must equal to 0. So from here, let's rewrite this expression and make VA the subject of the formula. So VA is minus MB over MA times VB. And we'll call this equation 1. So we'll use this again later. Now, let's look at the diagram and consider some of the trigonometry. So initially we have cart A, and that is the vertical, the line at which the weight is acting. And then we have the cord or the cable of length L and the block B. So this is initially when the system's at rest. This angle we'll call theta. So the vertical distance mark this in a different color in red. So this vertical height is L cos theta using some trigonometry. And afterwards, we have block A moving to the right with velocity VA, and the block a vertical distance directly below the cart A moving also to the right with velocity VB. So it's a distance L from the cart. So now let's apply the conservation of energy. So initially, the energy, kinetic energy T0 is 0. The system is at rest. The potential energy of the block V0 is equal to mgh. So the height of the block above its position directly below the cart A. So this is the mass of the block times acceleration due to gravity times h. And h is this, in this case, is L into 1 minus cos theta. So L minus L cos theta gives us this height above the rest position. This is L minus L cos theta. So the height of the block when it is pulled back above its lowest position, which is the position directly below cot A. So that's L minus L cos theta. So it's L into 1 minus cos theta. So as B, so this is initially, and then as B passes under A, we have a kinetic energy due to the cot, a half ma VA squared, plus a kinetic energy component due to the block, a half mb VB squared. So the kinetic energy of the system has contributing factors from the cot and from the block. And at this stage, V is equal to 0. So H here, in this case, is 0 when block B is directly below block A, cot A. So now the conservation of momentum tells us that T naught plus V naught, the mechanical energy is conserved. So T naught plus V naught is equal to T plus V. So what does this mean? This means if we substitute our expressions in, that mb times g times L into 1 minus cos theta is equal to the final kinetic energy, a half ma VA squared plus a half mb VB squared. And this makes sense. So essentially what's happening is that the potential energy in the block, when the block is released, is what results in a motion of 1, the block, and 2, the cart. So that potential energy is then transformed into kinetic energy of the block and the cart. So if we substitute for VA from equation 1, and we multiply that by 2, we get the following expression. We get that 2 times the mass of B times G times L into 1 minus cos theta is equal to MA. Remember, equation 1 is this equation here, is equal to MA into MB squared over MA squared times VB squared plus MB VB squared. So this is equal to, so we'll open out the brackets here, we get MB squared over MA plus MB, bringing out VB squared as a common factor. And so we can simplify this even further. This is MB multiplied by MB plus MA, the sum of the masses, over MA times VB squared. So finally, we can rearrange this and write an expression for VB. This is the velocity of the block as it passes underneath the cart. and VB is equal to the square root of 2 times MA over MA plus MB multiplied by GL into 1 minus cos theta. So now, using this equation and writing down our given data as follows, we're given that the weight of A is 60 pounds, the weight of the block B is 40 pounds, L is 6 feet, where L is the length of the cable holding the block to the cart, G is 32.2 feet per square second, and the initial angle of release, theta, is equal to 25 degrees. So we have enough information here to solve for VB. And if we solve for VB, we can easily solve for VA. So what we get from above is that so we'll also call this equation 2. For the expression for VB, we'll call equation 2. And so we can substitute our given data into this equation. So 2 MA over MA plus MB is equal to 2 times the weight of A over the weight of A plus the weight of B. The mass and the weight are related by the common acceleration due to gravity, and so we can write the two expressions as equal. And that's 2 multiplied by 60 over 60 plus 40 pounds, and we get 2 MA over MA plus MB to be 1.2. So now, using that and going to equation 2, we get that VB, so this is the speed of block B as it passes under block A, to be the square root of 1.2 times 32.2 multiplied by L, which is 6, into 1 minus the cosine of 25 degrees. And hence we get VB to be 4.66 feet per second, and this is to the right. So at the point at which it passes under block A, it is moving horizontally to the right. And VA, we said, is simply minus WA over WV, since the common factor is G, times VB, and again we have these values, so that's minus 40 pounds over 60 pounds times VB, which we calculated to be 4.66, and hence VA, the speed of the cart as VB passes under it, is equal to 3.11 feet per second, also horizontally to the right.